Today we're going to cover 6.1, the law of sines. And really our goal here in 6.1 and 6.2 is to figure out ways that we can relate sides of triangles that aren't right triangles. Okay, and we'll call those actually oblique triangles. Let's go ahead and figure out what the law of sines is, and we're going to prove it in the process. So the first thing I'm going to do here is actually try and make a dotted line to here, and hopefully that looks like that makes a right angle right there. And let's go ahead and call this height here h. There we go. And we're going to prove a few things about this, and then we'll move to the other triangle, which is technically the same triangle. So let's first compute sine of big A. Okay, so sine should be opposite over hypotenuse. So the opposite side here is the h, okay, and the hypotenuse is this side length here, b. Let's also compute sine of big B. And so if we look here, opposite over hypotenuse, we should have h over a. And what I'd like us to do from here is solve both of these for h. Let's go ahead and do that. So we get h is equal to b sine a. And with the bottom one here, we get h is equal to a sine of b. And now that we have two things that we know h is equivalent to, let's go ahead and set those two things equal. Okay, so we have b sine of a is equal to a sine of b. And all we're going to do here is we're going to divide both sides of this equation by a and b. So little a and little b. So on the left-hand side, this is going to leave us with sine of big A all over little a is equal to sine of big B over little b. And so this is actually half of our law of sines. We're going to get the other half right now. Let's go back up and look at the other triangle. And so we're going to form a different right triangle here. And let me switch colors. So I'm going to try and go straight down here. Okay, there we go. There's a right triangle. And let's call this side here h prime. Okay, because it's probably not the same length as h over there. So let's actually start off by computing sine of 180 minus c. And what we're going to do is we're going to use our difference formula for sine. This is equal to sine of 180 cosine of big C minus cosine of 180 sine of big C. Okay. And sine of 180, that's 0, so we're going to have 0, and then minus, and cosine of 180 is minus 1, so we have minus 1 times sine of C. And so this is just positive sine of C then. Now you might be wondering, Why is this all helpful here? Well, this is going to allow us to compute sine of big C. Before, we couldn't compute it because this triangle here isn't a right triangle. But if we're looking at sine of 180 minus C, well, that's actually this angle right here. And so sine of 180 minus C, this is opposite over hypotenuse. So this is H prime over B. And we'll actually solve this for H prime. But I'll do that in a minute. Let's also look at sine of B. So if we look at sine of big B, let's envision this actual big right triangle here, okay? So sine of big B should be opposite over hypotenuse, so that's H prime over C. And we can go ahead and we can solve each one of those for H prime, just like we did on the other side, except for it was for H. And so we get H prime equals B sine of big C. And H prime is equal to little c sine of big B. And what we can do is we can take these two and we can set them equal to each other. And that gives us B sine of big C is equal to C sine of big B. And if you finally divide both sides of this equation by B and C, you'll end up with sine of C all over little c is equal to sine of big B over little b. And so if we combine these two things that we found here, let's see what these two things are. This and this, if we combine this all into one big equation here, we have sine of A all over little a is equal to sine of big B over little b, which is equal to sine of big C over little c. And we will be using the convention that the capital letters are angles and the lowercase letters are side lengths. Now, this isn't the only way we can write the law of sines. It's actually also true if we used A over sine of A is equal to B over sine of B. So just the whole thing flipped over. And lastly, I want to make sure that you know what to use this for. When to use this. So you can actually use this thing to solve right triangles, but you don't need to. You have SOHCAHTOA. So this would be a little more work than you need to do. So when you really want to use this is when you have oblique triangles. So use the law of sines when working with oblique triangles. And all oblique triangles means is triangles that are not right triangles. All right, let's go on to our first example.